Okay. Okay, everyone. I'll try to briefly go over the content for this year. So last time, I think we have finished roughly here about the stellar evolution. And as I emphasized last time, the HR diagram is very important. So we can go a little bit further into this diagram today. So if you look in very much details, so you will see that there are two axes here. So the y-axis is something called absolute magnitude. So it's sometimes called like luminosity. So basically, it is a one-to-one conversion relationship. So I have a question here. So does anyone know what is absolute magnitude and what is a luminosity? Any volunteer to answer this question? Chloe, can you try to answer this?
I know like the luminosity is like basically the brightness of the stars. Spectral class, I think that might be like
How big it is?
I think that's hold on.
Oh, no problem. Yeah, okay. Yeah, I'll try to, yeah, I think you get some of the points. So luminosity is one way to measure how bright the star is, right? So that is correct. But in terms of the technical terms here, luminosity means the whole energy, all the energy that a star emit. So that is the luminosity. So we have a unit of like sun equal to 1 here. So which means that for this that is the solar luminosity. So all the energy emitted by the sun in 1 second. So that is the luminosity. And we have a conversion from luminosity to absolute magnitude. So if you are interested, you can look at the formula. So they have a one-to-one correlation. So you can see here, absolute magnitude. Well, it does not show which band it is here, because usually when you have a telescope and you are measuring a star, so you have different kind of filters, right? So using the filters, you will see different band, like from optical, from very blue to very red, and all the way to infrared. And if you go to very high energy, you have X-rays. So you have different band, but usually the absolute magnitude here is measured in some optical band, because that is the most easily accessible band here. So you know that absolute magnitude basically is the all the energy that emitted by a star in a certain period, usually 1 second. So this is the y-axis. So basically, this diagram tells you that a brighter star will be somewhere here. So it is in main sequence, right? And the x-axis is the spectral type. That is basically the color.
All right.
Yeah, so you can look at the picture here, and that tells you the color. So when it is, you have a very massive star, and it is in blue supergiant. So that tells you, well, it is blue, right? So that is how you determine the different types here. And when it evolves to other later stages, so it will evolve. So what it tells you here is that, well, so if you look at this branch here, So that tells you the absolute magnitude is very bright, but the color get much redder. So because when it is O type, it's very blue, and it's because it is very very hot. So it's very hot. So the temperature would reach something like 25,000 K. So that is very hot. But when it goes here, it is much cooler. So it can go to as low as like a few thousand K, like 2.5 K Kelvin. Yeah, so that is the range. And then you are supposed to remember the sequence here. So O, B, A, F, G, K, M. So there is a sentence to remember that. So Ethan, do you want to say it?
My dad taught me this. It's I'll be a fine girl / guy. Yeah, kick me. Yeah.
Yeah. So O being a fine girl, kick me. Yeah. So you can come up with another sentence that you can memorize it well. So yeah. So O star means it's very young, and it's
bright.
very big, young and bright. So that is the main sequence here. And M means that it's very small and very cool. So that is the M star. So when it evolves along the HR diagram, so if it evolves of the main sequence, so that is the main sequence here. The main sequence, because it calls main sequence because it is a sequence on this HR diagram. And that sequence tells you there is almost a one-to-one relationship between the absolute magnitude and the spectral type, basically the color. So when it is bigger, then and it is brighter, then it is hotter. So that is the relationship that it tells you about the main sequence. And when it evolves of the main sequence here, so you will see different kind of post main sequence stages. Yeah. So you can see like supergiant is here, and we can look into that later. And there is other branches here. And I think later we have something here. No. Here. Sorry, probably I missed it. Yeah, there is a HR diagram somewhere.
你先 zoom out 吧。
嗯
你这样子。
呃
这儿有。
Yeah, that is one cluster. That is probably one open cluster. M55. Okay. Anyway, yeah, there should be one later in this slide, so we can look into that later. For sure. Okay. Yeah. So this is about HR diagram. And the later part of this is about the deep sky objects. So there are 12 in total, and they are basically classified into 3 classes. One is star and the star systems, and the 2 is stellar remnant. So, what is the difference between the 2? So, anyone want to answer? What is the difference between the 2? What is the difference between star and the stellar remnant? Any volunteers? Nicholas, do you want to give it a try?
I'm not sure, but I think a star is like the ball of gas that generates energy, and the stellar remnant is what happens like after it dies, or like after it fades out, like exhausted.
Yeah, right. Yeah, very good. So I think you get a very important point here that the stars it will emit light, and the light is from nuclear synthesis. So basically fusion, thermal fusion.
Thermonuclear fusion.
Yeah, thermonuclear fusion. So it is usually like the hydrogen collide with each other on the very high temperature and a very high pressure. So they will merge into helium. And in this process, they will emit energy. So the energy source is from thermonuclear reactions, so fusions. And the stellar remnant, it had a different source of energy. So as you see here, there are like pulsar and supernovas and then planetary nebulas, etc., and X-ray sources. So they have different kind of energy sources. So they are not, well, some of them are from, for example, supernovas. It has a totally different energy source. So we can cover that later. And finally is the gravitational wave. So GW means gravitational wave. And the 150914 means that it was discovered in 2015 in September 14th. So that is how the name came in. Yeah. And those deep sky objects, I want you to remember the details of them. Specifically, I think they have already listed all their features here. So number one, what kind of what constellation it is in. So for example, you see that the House-Taylor pulsar here, right? So you need to remember, yeah, it is in the constellation that is Aquila, right?
The eagle.
Yeah. Well, at least you should put this in your cheat sheet so that you can look it up. But in the best situation, you're supposed to remember it. And the second thing you need to remember is the object type. So is it a star or a stellar remnant? So if it is a star, what kind of star? If it is a remnant, what kind of stellar remnant? So what evolutionary stage it is right now? So is it in like a red giant state or in a white dwarf state? Is it a pulsar or is it a supernova remnant or etc.? So look into all these things and try to make the link between the object and all these features. So like for example, the House-Taylor pulsar. So it is a very special object. So it says here that this is the first of its kind ever discovered, right? So how special it is? It won a Nobel Prize. So if you are aware that right now we are announcing the Nobel Prize for this year. So basically, AI got the Nobel Prize for physics and the Nobel Prize for chemistry. So that is a big thing. But 50 years ago, so pulsar won the Nobel Prize for physics. So, and these two persons, House and Taylor, they won the Nobel Prize. So they discovered this House-Taylor pulsar. And why it is special? Because it is a pulsar rotating with a neutron star. So it is the first of this kind. And yeah, so using what is a pulsar? So for example, so do you understand what is a pulsar? So the pulsar means that it emits energies. Well, the physical model is here. So it is rotating. It is basically a neutron star, but with magnetic field. So it had some polar emissions along the polar directions. And when the pole well, when the jet emit to the Earth, and you see a very bright emission, right? And when
With the
it
full spectrum.
rotate away, you see it is very dim. So you can see the curve of the emission in radio. It will change like this, right? And it is very periodic, and it very precise, because the neutron star rotate very stably, so it will not change its and the energy will not lose much. But you can see here, well, but when you have two rotating to each other, and you have this one rotating itself, so it will gradually decay. So it will lose energy, and the two will move closer and closer. And when they move closer, they rotate faster. So that is why you can see here that the time gets the period gets smaller and smaller. So that is called the orbital decay of the binary system. So this is precisely aligned with the general theory of relativity, because in Newton's theory, you will not see these, but in general theory of relativity, you have this decay. Okay.
忘了吧，已经5:50了。
Okay, so for the 12 object, please pay close attention to the object type, what kind of star or star remnant it is, and why they are special. So try to put that down in your cheat sheet. Okay. So we have 10 minutes left. So let's use the final 10 minutes for some Q&A. So if you have any questions, please feel free to ask.
I wasn't here for like the first part of the meeting. What did we cover?
The first half of the meeting, we were watching the video and trying to learn what is in the video. So
Okay.
you do not miss anything. But make sure you watch the video yourself and make the cheat sheet yourself. Okay.
Okay.
Great. And you know that we have an invitational this Saturday, right? At 11:30.
Yes, I
So
do know.
arrive a little bit early so that you can log in before 11:30, and work with your partner, because that would be your how you solve the problem together. Yeah. And don't click the take the exam now, and wait until Saturday to do that.
Okay.
Okay. Any other questions? Yeah, if no more questions, I have put all these slides in the Discord channel. It is here. Yeah. So you can see it here. So this is a Google Drive link, and it has all the slides that is showing in the video. But you cannot take this with you as a cheat sheet. So try to summarize what it is written. And we have added something here because we want to show the whole constellation and where it is located, right? So for example, for the Haus-Taylor pulsar, it shows it is here, right? And it is in Aquila. So Aquila is here, and the Haus-Taylor pulsar should be somewhere here. So it is not the brightest, not surprisingly, because neutron stars do not emit a lot of optical light. Then you can think, well, you cannot see it, right? Then how do you find it? So that is the question. And that could be a potential question in the exam, right? So because all the stars here, they are very bright, right? So the bigger the star, the brighter it is. It is very bright, then you can see it. But for the pulsar, you cannot see it. Then how do you find it? Using what kind of telescope can you observe pulsar? That is the question. Do you want to give it a try, Ethan?
No.
How do you find the pulsar? Do you remember how they find what telescope did they use to find the House Taylor?
Guess you can use the I think it emits some X-rays,
No,
gamma rays,
no.
infrared. Oh, no, radio,
It's
radio,
in
radio.
radio. Yeah,
Radio.
in radio it's very bright. And this was found by Arecibo. So it is a 300-meter telescope in Costa Rica. And it recently collapsed, so it is not in use now. But it made the discovery, and it won the Nobel Prize. So yeah, it's very important discovery. Neutron star and pulsar. Okay, let's call it a day. And again, make sure you have your cheat sheet ready for the Saturday. And well, I will see you on Saturday.
Thank you.
Thank you.
Thank you.